Good morning, everyone. I'm
Good
Rajashri,
morning.
Principal of DCI Institute of Technology. I'll just take a minute to do some introduction. I'm audible, right?
Yes, yes.
Okay. So I'll start with a small introduction about ERNDCIT per se. That is, ERNDCIT is a academic arm of CDAC, Thiruvananthapuram.
Okay.
We are basically offering to cyber forensics and information security. So they are full-time programs affiliated to Kerala Technical University here. And this webinar series was primarily intended for our students. We thought all other interested people, you have very interesting and interactive experience here through this webinar of ours. As you all know, today's topic is accelerating deep neural networks inference via edge computing through FPGA. So the resource person for the day is Darshan C. Ganji. Am I audible?
Yes, yes, I can hear you.
Yeah. So yeah. Darshan is a project associate in the Department of Electronics Systems Engineering, IISc. His research work includes AI hardware and high performance computing. His passion lies in parallel computing, particularly in many-core computing and the use of accelerators in combination with multi-cores to optimize performance. He's keen to explore the things on end-to-end system architecture definitions, hardware software co-design, and performance optimization for multiple generation of accelerator systems. So on behalf of ER&D CIT and on my personal behalf, I extend a warm welcome to Darshan.
Thank you, ma'am. Thank you so much for inviting me.
We are very grateful to you for your willingness to share the knowledge with all our students and also all interested people.
Okay.
How many are there, Divya,
Ma'am,
today?
till now 58. So many are waiting to join. They will join. I think we can start the session
Okay,
now.
okay,
Okay. Thank you, ma'am,
right.
for the words.
So I wish all of you once again very interactive, informative learning session. And I request Darshan to start the session. I am sure more people are going to join, but we'll
Yeah.
start the session right away.
Sure, ma'am. I'll start. So, can you see my screen?
no, Darshan. You can go to the present now.
Yeah. Exactly. So, how about now?
Yeah, it is coming.
Okay.
Yes, you can put it in slideshow.
Yes.
Yes, it's okay.
Okay. Yeah. Shall I start, right?
Yes, you can start.
Okay. So, good morning, all of you. Good morning. Thanks for joining this session. Today I'll be going to present a session on accelerating deep neural networks inference via edge computing. So I targeted FPGA as a deployment platform here. My agenda is my agenda is to walk through the algorithms, right? So algorithms for efficient inferencing. Okay. So I hope you have some knowledge on deep learning, neural networks and machine learning. So if not, I'll be covering some basic part of what the neural network training is and what inference is, right? So yeah, so I'll be discussing with efficient algorithms. Okay, so like how we'll get good efficient inferencing by applying these algorithms for neural networks and how it enables to meet the deep learning with the edge computing, right? So I hope you'll be knowing what edge computing is, right? So in spite of going for cloud to get a response and to get a compute response, you just enable your edge platforms like Raspberry Pi or Zetson Nano, FPGA, right? So GPUs to compute and to accelerate and to get to minimize latency and maximize the throughput of your deep learning applications, right? And then I'll be covering some hardware, right? So some specific hardware by MIT, Stanford, and right from Google. So for they are the ASIC, right? So I'll be covering specific hardware for each particular hardware. So what is uh, you know uh, the speciality of each hardware, right? So and then I'll be discussing with a YTCI, right? So Xilinx YTCI platform to deploy your deep learning models onto your FPGA. Okay, so this will be my agenda. Let me go ahead. So let me introduce myself, right? So I'm Darshan CG from I'm a project associate in Department of Electronic System Engineering in Reconfigurable Computing Lab. I work under Professor L.M. Patnaik, right? So he's a adjunct professor, and he's a INSA's senior scientist, right, in NIAS, right? So in Indian Institute of Science, right? So I work on basically hardware acceleration. Okay, so for particularly for AI, right? For deep learning applications, and right now actually I'm also working on the compiler design, right? So compiler for multiple targets, like for FPGAs, for GPUs, for CPUs, and other neural network processor engines. Okay, and also I have some experience on dealing with the high performance computing, for GPUs. You might be knowing about CUDA, and OpenCL, right? So I have some experience with working on these architectures. Yeah. So with this small introduction, I'll go ahead, right? So this is actually the deep neural network structure overview, right? So you might be knowing, right? So one is ML and other is deep learning. Okay, one is machine learning and other is deep learning. Okay. So in machine learning, what happens is you have algorithms. Okay, you have k-nearest algorithm, you have logistic regression, linear regression. So these are some algorithms, so which is used for prediction. Okay, so neural machine learning AI is all about prediction. Okay, so it's basically used for predicting and for generative modeling. Okay, for generative applications, right? So what happens is in machine learning applications, so you will not be through machine learning algorithms, you will not be able to implement it for advanced application, right? So for image classification and for face recognition in your mobile, you have face recognition, right? So those has to be a complex algorithm, right? So there comes a neural network, right? So all the deep learning, prospective deep learning covers majorly the neural networks, right? So you have a convolutional neural network for image, right? For image and recurrent neural network, LSTMs, right? For sequence modeling, in the sense for speech, right? So for speech audio, right, you have RNN LSTM, right? And then you have GANs. Okay, so generative adversarial network for generating an image, right? So you have a app called face app. In some time it got famous in last year or so. It takes your image and restructure and it generates your age, your other version of the image. Okay, like if the face app used to take the image of yours and it will generate the other image of different aged. Okay, so if you put the age of 50 or 70, then it will create your image of that particular age. Okay, so these are all the neural networks. Okay, so what happens in neural networks is that you first train the neural network. Okay, so you will train your neural network, right? So the neural network is exactly the same of your brain. Okay, so it mimics the brain. You have synapse, right? You have neurons, synapses, right? So it actually mimics the brain. Okay, so you might be knowing the Geoffrey Hinton, right? So he's a father of actually the AI. So he created more neural networks. Okay, so Geoffrey Hinton, you have Andy Kuhn, you have you have Andrew Ng, Fifi Lee. So these are actually the leaders of AI who did a lot of research on neural networks, and they have proposed different algorithms for the prediction. Okay, so actually now what's happening, so I'll say the present reality. Okay, so many people are going to AI. Okay, so AI software. So I'm speaking with a software. Okay, AI software. Okay, only with respect to coding and algorithm programming. Python, TensorFlow, Keras. Okay, Cafe. So they are using these frameworks, and they're building the real world problem. They're working to solve the real world problems. Okay, on the other hand, what's it is trending is the AI hardware field. Okay, so the AI hardware field is actually the trending field. Okay, the it's a trending field now. It's it will be a boom for next 10-20 years. It will be boom. Okay, no, as it is a CDAC, right? So I'll be dealing with the algorithmic hardware perspective, right? Not only the algorithms. So when I'll be covering algorithms, so I'll be covering the hardware. Okay, hardware perspective also. Both algorithm, hardware, co-design approach for deep learning. Okay, so yeah, as I was saying, the the AI hardware field. Okay, so there are lot many research is going on, lot in terms of AI hardware. Okay, so as you see in Intel, now I'm saying a general. Okay, so general knowledge on this is not the slide how I'm covering. So I'm just going the slide the general. Okay, so how industry is working on to AI hardware, and how the the demand is there. Okay, so if the 1,000 people are working on the AI software. Okay, so the deep learning and solving the real world problems, uh, hardly will get around 30 to 40 working on optimization on AI hardware, right, on particularly on FPGA, right? So in AI hardware, so there will be a lot many platforms. Okay, so the first comes GPU, right? So GPU optimization, right? So Nvidia is the pioneer of accelerated computing, right? So they have their own frameworks, they have their advanced architecture, right? So before just before 1 week they have released the Ampere. Okay, so Ampere architecture, so which is particularly meant for deep learning application. Okay, yeah. And another is another platform is the Xilinx FPGA platform. Okay, so Xilinx is also investing huge on particularly on AI hardware. Okay, so they want to they have their own compiler technologies, and they have they are coming up with more hardware, right? So more hardware specifically for deep learning application. Okay, so what happens is that only targeting the hardware, designing hardware and coming up with a new architecture in the hardware is not only the the good solution. Okay, but you need to have the frameworks, right? So you need to have the frameworks for for the customer to use their hardware, right? So if Xilinx designed the custom hardware for custom FPGA, if it is targeting the deep learning application, so they have to come up with their own APIs, right? So like the YT's AI, what they have. So I'll be covering with what YT's AI, right? So they have YT's AI as a platform, particularly for deep learning uh, application, right? So the customer who want to deploy their model on FPGA, right? So they don't need to worry about designing their IP, designing system design, or of any neural networks on FPGA, right? So that is very difficult task, right, for the customer, right? So they need to only deploy the deep learning model onto their on the FPGA, right? So what is the disadvantage of FPGA, right, for deep learning, right? One thing is FPGA can't be used for training, right? So they can be used. I'm not saying they will not be used. They can be used, but uh, the GPU has major advantages on the uh, with respect to deep learning training. Okay, so they have taken all the market share, maximum around 90% of market share of the deep learning training. Okay, as I was saying here, right? So you have to train. So this is what the training, the phase of this one. Okay, so this is where the inference happens, right? So you want to deploy, right? So assume if you have a face recognition. In your mobile, right? So that is one of the deep learning application, right? So face recognition in your mobile, right? So they before deploying on your mobile, right? So before deploying on your mobile, so they have to be first trained, right? So with a data set they collect, they have to be trained on these data sets, right? So the neural network has to be trained on this data set, right? So this phase involves a huge number of computation, right? So this is very compute intensive task that will be happening, right? So people will be using the AWS, right? So you have a Amazon AWS, you have a Google Cloud platform, right? So they use the GPU at the back end to train the deep learning models on the GPUs, right? So they give a platform, the AWS and Google Cloud platform, right? So the GCP, right? So they give the platform to train a deep learning model on the GPUs, right? So GPU actually it has a lot of cores and it supports parallelism, right? But when it comes to FPGA, of course FPGA is less speed than GPU. So but what's the main advantage is it consumes less power when it comes to GPU, right? So GPU will will dissipate a lot of power while computing, right? So if you take any GPUs, right? So in your system, right, in your PC or in your institution also, right? While you're training the model, just see the the heat dissipated, right? So that is a main the disadvantage of the GPU, right? So that will be overcome by the FPGA, right? So FPGA design will overcome the power consumption. Okay, and the main also the main advantage of the FPGA is that you can customize your precision, right? So you can the precision in terms of the bits, the number of bits to represent the number, right? You can customize your design for int 8. Okay, you can customize your design for FP16. So that flexibility you are going to have in FPGA design, right? So that flexibility is it's bringing a very useful for the designers, right? For the for high throughput, right? So you can assume now deep learning models are evolving, right? So every day, every week they are coming, the Google Brain team and the Nvidia research and Facebook AI team. So they are coming up with they are doing a lot of research on neural networks. So they are coming up with a lot of efficient state of the art neural networks, right? So while deploying on FPGA, right? So assume the Facebook AI launched a neural network today, right? And also it had launched the neural network last month. Okay. So what happens is that when you are deploying your deep learning model onto your FPGA, right? So the one designed the neural network which was designed by Facebook last month supports only FP16, okay, FP16 representation, right? FP16 precision. But the neural network designed by Facebook AI team today may support int8 also, right? Int8 also, right? Which is very low, which low precision, right? So which is very low precision and which takes less bits to represent the number, right? So there you are going to compress the model, right? In int8 mode, you are going to compress the model, and you can design the architecture supporting for int8, okay. Right, so that flexibility is going to give on FPGA, right? But it will not it will not give in ASIC, right? So ASIC is fixed architecture, right? So once it supports for FP16, then you can't run your int8 deep learning model on that ASIC, right? So that flexibility the FPGA is going to give for the deep learning deployment, right? So I'm speaking with respect to the inference, right? So training always the GPU and TPU wins, right? But in terms of deployment, so that is why the inference at the that is what the title name here, the inference, right? So there are two phases, right? One is training and another is inference. Okay, so training is you are training the neural networks, right? So you are doing huge computation, and you are coming up with a representation which actually the which gives the right prediction. Okay, so the after training you'll get a hypothesis. Okay, so that hypothesis will be deployed onto your edge device, right? So yeah. So as I was saying, right? So I'll be covering majorly with respect to the the deployment, right? So the deployment phase, the inference phase, not with respect to the training. So which where FPGAs, FPGAs, Xilinx, they have Alveo boards also. But in terms of market share and in terms of the accelerating stack, the Nvidia GPUs they have, that makes them win over the race of deep learning training. Okay, yeah, so let me go ahead with my slides. So if you have any doubts, right, you can unmute yourself, and you can ask me at any point of time. Okay. Okay, so the first challenge is the model size. Okay, so when you're deploying, right, so when you're deploying your after training, so when you're deploying on any hardware, right, in particularly in edge computing, not in cloud. Okay, so one is the model size. Okay, so the model after training, the deep learning model will be around 500 MB, 600 MB, right? But if you want to use your on-chip memory, right, on-chip cache, right, efficiently, so you need to compress the model. So you need to bring your 500 600 MB of your deep learning model into 50 MB, 60 MB of your deep learning model, right? So that is actually the first challenge, right? So if you want to deploy on your mobile, so that has to be compressed, right? So that has to be compressed. So majorly first three algorithms, what I'll be discussing is majorly with respect to the compression, right? So model compression, like you have video compression, audio compression technique. So I'll be discussing the algorithm specifically for deep learning model compression. Okay. Yeah, so this is actually one of the the challenge which needs to be overcome, right? So one is with respect to model size, and next is with respect to the energy consumption, right? So energy consumption, right? So what happens is that when so assume, right? Let me assume you have a DRAM, right? So you have DRAM here, right? So and you have a on chip cache here, right? So this is small and this is DRAM. So DRAM actually it consumes more power, right? More power, because DRAM is built by capacitor, right? Capacitor and transistor, but it's only cache is only with designed with the transistor, right? So there is lot of energy consumption, right? So capacitor dissipation, charging, discharging, charging, discharging. So this DRAM, it takes a lot of power, right, compared to the cache. But in terms of the access speed, the cache is very much the access speed of cache is very much high, compared to the DRAM, right? So DRAM has less access speed when compared to the cache, right? So one major advantage of a model size is that, so instead of storing your deep learning models on this DRAM, how about storing your deep learning model on the cache, right? So cache is near to your processor, right? So this will first this will decrease the access time to access this the memory, right? So instead of going to DRAM to access the data, you just access access the data from the cache, right? So increasing your speed, access speed, and also in terms of the energy consumption, right? So while designing any hardware, right? While designing any hardware, so one target is that, so one thing you have to be the goal has to be is that one is with respect to the the storage, right? So where you want to store, right? So if your design will be storing your on DRAM, so you have to be careful about the energy it consumes, right? So that will be one goal of the design of your hardware. Next is with respect to the sparsity, right? The sparsity, right? So so deep learning is all with respect to the matrix multiplication, right? All the advanced linear algebra, right? So at the back end, it's all matrix multiplication, right? So GEM, so you might be knowing about GEM, right? So general matrix multiplication. So all is with respect to matrix multiplication, right? So how about you compute in a sparse way, right? So you have a matrix, right? So you have a it's a, I hope you'll be understanding, right? So it's actually the difficult to write down on the screen here. So you have a matrix, right? So how about removing some the data, right? So you have some number which is going to less affect for the deep learning, right? So how about removing, assume it is around point 1, right? It is around 0.1. So how about making this to 0, right, instead of 0.1? So this is actually less effective, right? How about making it to 0, right? So this amount of so this is what the sparsity is at, right? So you make this as 0, right? If the weight is less effective, you make this as 0, right? So you will get a sparse matrix, right? So you will have a zeros in this one, right? So how about removing this multiplication, right? So and only compute this computation, right? Only this on this data, right? So you are decreasing the computation, right, here. So you are increasing the speed of computation, right? So you have to you have to take care of this sparsity into account while you are designing the hardware, right? the hardware for the deep learning application, right? And other target is the precision, right? So whether your deep learning model, your chip wants to support for int8 or FP16 or or FP32, right? So you have to be you have to be specifically keep in mind about the precision, right? So one is with respect to what I said, the memory, the memory, and another is with respect to the sparsity, right? The sparsity, right? And another with respect to the the precision, right? So int8 or FP16, right? So these are some goals you have to target while you're designing your IPs, right? On your FPGAs, right? For specifically for deep learning applications, right? I hope you are all understanding now. So yeah, second challenge is, as I discussed, the energy efficiency, energy, right? So energy. So if you see the deep learning, right? So if you deploy your model on your mobile, so it's taking it drains the battery, right? So you have to be efficiently apply some algorithms to overcome these challenges, right? So energy efficiency and model size, right? Yeah. So where is actually the energy consumed, right? So uh, the here, if you see the energy, the relative energy cost here. So your DRAM, right? So your DRAM is consuming much more. So this is only with respect to access, right? So this is all the computation, right? This is all the computation. Here you are doing computation. So in last two, you are accessing the data, right? If you see the data access, right, here in your DRAM, the energy, the amount of energy consumption is the 2x, right? When it compared to the other the computation, right? So here you are computing, right? The multiplication and the addition you are computing right here. So if you compare the energy taking for computation with respect to the energy took for access, okay, so here you are getting more your energy is consumed more here, right? So you are so what's the solution for this, right? So how about the you're decreasing the access of DRAM and increasing the access of cache, right? So as I said in my earlier slide, so you compress the model, and instead of going for DRAM, you go for the cache, right? So for storing your deep learning model. Okay. Yeah. So this is one of the major challenge, right? So the power consumption is one of the major challenge uh, in deep learning application, right? So yeah. So if you have a large model, okay, so for different application, right? So this face recognition in your mobile is bit uh, less, right, in less in size when you compare to more algorithms, right? So you have a the recognition on the video, right? The real time, you might be heard about YOLO v3 SSD, so those are the model which are used for real time object recognition, right? So while you are doing on real time, so you need lot of computation, right? So you need lot of speed, and you need lot of the throughput to take the frames and to apply the deep learning algorithms on that and give the results, right? So when you compare to face recognition, so this real time face real time object detection is much more larger in size when you compare to the face recognition, right? So when you have a large model, so you need a more memory reference, right? And more energy is consumed, right? So assume the DRAM is large, right? The size of DRAM is large when you compare to cache, right? So if your model goes on increasing, so obviously you need to store your model onto your DRAM, because cache is less in size when you compare to the DRAM. So the one important the solution is a compression, right? So yeah, in my next slide, I'll be showing the algorithms for the compression, right? The quantization, pruning, right, etc. Yeah. So when it comes to the hardware family, right? So you have the general purpose and you have a specialized hardware, right? So general purpose is you can use for any application, right? So you can use GPU for graphics rendering, right? So you're playing game, right? So at the back end you are using the GPU for the graphics, high-end graphics rendering applications, right? And also the CPU, right? You can use the CPU both for graphics also, and you can use for computing also, like was the GPU, right? And when it comes to the specialized hardware, what happens is you have a FPGA and you have a ASIC, right? So here, uh, so here in GPU and CPU, you are just using the hardware, right? So as I hope you have some experience on designing FPGA, on designing system designing with FPGA, right? So when you see with respect to GPU and CPU, you just use the hardware, right? You're using the hardware, but when it comes to FPGA, you're designing your hardware, right? I hope you are getting the point here, right? So here you are using the hardware, but here you are designing your own architecture, right? On the FPGA, right? So you have also the ASIC, right? So this ASIC I'll be discussing after discussing the algorithms, right? I'll be discussing the ASIC, right? The specialized hardware for AI from MIT and from Stanford, from Google, right? So I'll be discussing, right? So what in so what they have targeted for designing this ASICs, right? Yeah. Let me discuss with algorithms, right? So I think it's better to note it down when from now on, because it may be new for the many people, because lot many working on the hardware, only hardware, but not on AI hardware. So it's better to note all the algorithms for what I'm discussing and hardware. Yeah. So let me discuss with a pruning, right? So what is pruning, right? So if I have a deep, your neural networks here on your left side. So what is pruning, right? So you just remove the less effective connections, right? You just remove the less affected connections, right? So as I said in my earlier slide, right? So if the weight is around your zero point 0.1 or 0.001 here, so this will be less affecting, right? So this is the floating point, right? So the compute requirement for floating point is more, right? So why can't you remove this weight, and you reduce the computation, right? So accuracy, so of course your accuracy will be going down, but the trade-off will be there, right? So if you see the performance gain, right? So if you see the neural network connections here, right? So you are removing the unaffected weights, right? So you are getting the sparsity of this one, right? So this is dense, this is dense, and this is the sparse, right? So a lot of connections have been removed, and your the storage will be reduced, right? So you're zeroing out the the connections here. So you're reducing the memory, and you're reducing the computation requirements, right? So yeah. As I was saying, right, there is a trade-off, right? So if you see the speed up you are getting in terms of the computation is more with respect to the decrease in your accuracy, right? So of course you might be getting the reduction in your accuracy, but the amount of gain in computation is much more higher than the amount of reduction in your the accuracy, right? So yeah, so this is the trade-off. What I'm saying here, right? So this is the trade-off, right? Yeah. So yeah, so the pruning is removing the less effective the connections in your neural network. So as a result, you are getting the sparse the sparse representation of neuron with less decrease in accuracy, but more increase in your speed up, right? Computation speed up, right? Yeah. So if you see the after pruning, right? So this is the original before pruning. But if you after the pruning, so the if you see the result, right? So there is no much decrease in the accuracy, right? So if you see so this is the application of image captioning, right? So image captioning in the sense you are giving the image to your neural network, so it is predicting the action of what is there in this image, right? So what is happening in this image, right? So that is also on the intelligent, right? So that is called the image captioning, right? So the deep learning model is telling so what is happening in this image, right? So in this image, right? When you compare to the prediction before pruning and after pruning, so it's almost same, right? So and it's almost same, right? Yeah, so it's almost same. So no decrease in accuracy, gradual decrease in accuracy, right? You're representing your neural networks in a sparse way, and your storage will be reduced, and your complexity will be reduced, and the computation will be reduced. Yeah. So one more thing I want to say is that so why I am discussing these algorithms, right? So is that so if you do any projects, right? So if you do any your projects using your Xilinx FPGA or some system design you are doing with respect to the algorithms of deep learning you're implementing on your FPGA with using RTL or using the HLS. So you have to take care. You have to implement all these algorithms so that your design will be will be in a sparse way, and your design will be in efficient way also, right? So your design will be in sparse way also, in your design will be in efficient way also, right? So yeah. So while you're doing any projects, right? So you can implement this the less precision and pruning low rank approximation while you're designing your applications on FPGAs, right? So that's why the algorithms are very important, right? These algorithms are very important, right? So assume if people have been implemented this three algorithm with one paper, you have one IEEE paper, but if you implement whole this one, right? So you'll be getting much more accuracy and much more betterment with respect to speed and the latency, right? So there you can come up with a different paper, right? So applying these algorithms, right? So these algorithms are very important, right? So yeah, so I was discussing the prediction after pruning and before pruning, right here. Yeah, in your in human brain also, right? So there is a pruning happening, right? In your human brain also the pruning happening, right? So when you're newly born, right? So this reference I took it from this paper. So when you're newly born, you're taking you have 50 trillion synapses, right? And after you are 1 or 2 year old, so you will have a 1,000 trillion synapses, right? When you are around 30-40 year, So your network will be pruned, right? Your synapses will be pruned. But accuracy is not decreased, right? So your thinking is thinking ability is not reduced, right? This is what the analogy of the neural networks you have, and the synapses pruned in your brain, right? Yeah. Next, I'll go with the weight sharing, right? So this is this is also one of the efficient algorithm for deep learning application, right? So what you are doing here, right here, so you're representing all these numbers with a similar number, with the same number, right? So this, if you see here, right, 2.09, 2.1 to 1.9 to 1.87. These are all in the difference is in small range, right? So why can't you represent this floating point number in integer, right? So this is integer, right? So this is floating point, right? So you represent your number, your weights, right? So your weights in integer, rather than going for representing with a floating point, right? So your floating point takes more amount of computations, right, when you compare to the integer. Yeah. When you're designing, right, so you have to keep it in mind about the lowering of precision, right? Yeah. So the before weight sharing, your weight representation would have been the discrete, the continuous, right, like this way. But after pruning, your weight distribution will be in a discrete way, right? Your weight distribution will be in a discrete way, right? So you're removing some, you're bringing back your floating point into the integer, right? So you're getting the discrete representation of the weights, right? Yeah. So next algorithm will be Huffman coding, right? Huffman coding. So I think you might be knowing about this Huffman coding in your in your BTech, or of course in your MTech also, with this Huffman coding is used for video audio compression. Okay, for right. So what is the intuition behind Huffman coding, right? You use more bits to represent for infrequent weights, and you use less bits to represent for the frequent weights, right? So you are decreasing the amount of the number of bits to represent, right? For your weights, right? So you are decreasing the the bits, right, and you're increasing the speed up and the amount of memory required to store the deep learning model, right? So this is also one form of the compression technique, right? So till now I discussed about the pruning, the one of the interesting algorithm, and another one is the weight sharing or the quantization, and next is the Huffman coding, right, which is also used for compressing your deep learning audio video compression, right? Yeah. So next algorithm is with a low rank approximation, right? So what is a low rank approximation, right? So you have a neural network, right? Here you have a neural network. So how about bringing this complex representation into two simpler representation, right? So yeah, so you are bringing this representation, this complex representation into two simpler representation, so that you are enabling the parallelism, right? So you can compute this part in one core, in this part in another core. You are enabling the parallelism, right? Enabling the parallelism, right, to compute, and it'll, of course, you'll speed up you speed up your computation, right? So yeah, you might be heard about singular value decomposition, right? So in your mathematics, right? So in your linear algebra, you might be heard about eigenvalue, eigenvector. But now I'll not be covering in depth of what eigenvalue, eigenvector those requires a separate session to discuss about, right? So this singular value decomposition and the eigenvalue eigenvector. So these are some advanced mathematics, right? So advanced linear algebra concept, right? So you can go through that, right? So applying the singular value decomposition on to this neural network, so you'll get a result like two simpler matrices, right? So two simpler matrices, so that you'll compute those two matrices with parallelly, right? So you're increasing the speed up, right? Yeah. So next, algorithm is with WINOGRAD convolution, right? So I think you can you might be knowing about the convolution, right, in your curriculum. So what is convolution, right? So convolution is it's a sliding and multiply accumulate, right? So the computation is heavy, the compute requirements is more when you compare to some other FFT, right? You're bringing back to some domain, and you're computing the convolution, right? And you're getting the same result, right? Right. So yeah. So if you see the Winograd transformation, right? So it's almost similar to the Fourier transform, right? So you're bringing your image and your filter to the different transform. Also your filter to the different transform, and you are bringing your image and filter to the same dimension. Okay, so this is 4 into 4 and 4 into 4. So instead of doing the sliding multiplication, addition, accumulation, so what you are doing here is the point was only the point was multiplication, right? So this one is multiplied with this part, and this part is right, this part is multiplied with this part, and then you are just adding, right, and you are getting the result, right? Instead of doing the pointwise multiplication and sliding addition, right, on image, with a filter, you're bringing back you're applying some transformation to the image and to the filter, and you represent in some domain, right? And instead of doing the sliding multiplication and accumulation, you just do the pointwise multiplication, right? Pointwise multiplication, right? To you avoid the sliding, right? So you'll as a result of this the algorithm, so we'll be getting the result as this one, right? So after the pointwise multiplication addition, you will be getting the result as this one, and after this one, you just do the inverse transform, right? So the what transformation you applied here, you just do the inverse of it, right? So you just do the inverse of this transformation here, bringing back the same result of the native convolution, right? So if you do the native convolution of these two, you will get the result, right? You will get the same result as this one. And also if you do the convolution with this Winograd implementation, you'll be getting the same result, but with a less multiplication, right? So yeah, so this is one of the advantage of Winograd convolution, right? So this is used in many frameworks, right? So convolution frameworks, right? So this is used in your image processing, right, in your computer vision applications. So this is this technique is widely used. So this is only used for convolution, right? So not for your sequence model, right? So sequence model in the sense RNN and LSTM. So this is not used for RNN and LSTM for speech, for voice speech recognition and of course and other sequence model application. So this is only used for your image related intelligence, right? So your face recognition, your image automatic image captioning and other techniques, right? So your GANs, right? So image transformation, right? So there you can use this Winograd transformation, right? So which will significantly reduce the amount of the multiplication required. So this will gradually decrease the amount the number of multiplication required, right? Yeah. So till now I covered with different algorithms for efficient inference of your deep learning model. Now I will cover with hardware, right, from different research institute, right, by MIT, by Stanford, by Google, right, and the China Academy of Science, right. So this was the IRIS, right. So this was the IRIS from MIT, from grouping under Vivian SG. So Vivian SG is a she's a researcher working on the hardware for AI hardware in the field of AI hardware in MIT. So under her group, so this was designed, right. So this is a IRIS Iris chip for deep learning, right? So what was what the main goal of this one was to the the access. Okay, so as I discussed in my earlier slide about the design goals, right? When you're designing the deep learning chips, you have to keep three goals. One is with respect to the sparsity, one is with respect to the access, right, from DRAM or on chip, and one is with respect to the precision, right, int 8, FP16, etc., right. So iris, so the MIT team, their goal was to accessing using on chip more rather than using the DRAM, right? So which takes a lot of computation, right? Which takes a lot of the power and access time, right? That was their design goal of the MIT, right? So the access, the memory access, right? And about the China Academy of Science also, they have this this chip, right? So they also targeted the same the goal which MIT followed, right. And when it comes to the Google, right, I think you might be heard about the tensor processing unit, right. So this is the computation, the computator for the GPU, right. When you're training your your TPU is a main competitor for the GPU, but in terms of market share and all, I think GPU is more way ahead when compared to the Google, right, with their TPU, right. Yeah, so they have designed they have designed their ASIC, deep learning ASIC, keeping in their mind about int 8 mode. Okay, so int 8 precision mode rather than FP32 or FP16. So they have considered the 8-bit form of representing, right. And when it comes to Stanford, they have a EIE, efficient inference engine accelerator, specifically meant for the deep learning application. So they came up with a sparse sparse representation, right. So they avoid the multiplication of the zeros, right. So they prune the network, and they avoid the computation of the sparse the sparse the zeros in the sparse matrix, right. So they avoid the computation, and they bring the the significant amount of speed up, right. And also this these ASICs, right, so this consumes less power, right. So they consumes less power when you compare to the GPUs, right. So GPU will take more power when it compared to the FPGA or the ASIC, right. So the main disadvantage of ASIC and FPGA is that ASIC over FPGA is that so ASIC is fixed, right. I hope you're getting the point. ASIC is fixed, right. So when you create the application for int 8, right here, so it only supports int 8 precision, right. So this assume your if you take the Google TPU, that is only designed with the int 8 precision, right. you can't run your model FP16 model on this TPU, right? On this TPU, you can't run your F16 model on the TPU. So that that's the main disadvantage, right? So while you compare your that to FPGA, so FPGA gives the flexibility, right, of your design, right, with respect to the intake or FP16 for separate model, right? So that that flexibility you are going to get on your FPGA, right? So that's one of the advantage of FPGA, right? So this can be used for the upcoming the state of the art model, right? So this may support for so some models, but to support for other models, they have to come up with other version of TPU to support for the different models, right? So that is one of the different that is one of the disadvantage of the ASIC or the FPGA, right? Yeah. So when it comes to FPGAs for AI, right? The FPGAs, the GPUs will be, of course, the GPUs are, of course, the fast, right? So in terms of training your models, GPUs wins over FPGA in terms of training, right? But when it comes to deploying, right, on if you want to deploy your deep learning models on your self-driving cars, okay, self-driving cars and drones, right? So there, what you can do is, you can deploy your deep learning models on FPGA, and you can use it for the drone and your self-driving cars, okay. Xilinx is doing more. They have customers with automotive domain also, and so they are using. They're coming up with a new innovation, right? So with respect to the compiler technology also, right? So as I said, right, so the design must not only with respect to the hardware, right? So the design also has to be with respect to the frameworks, right? So if Xilinx comes with a own hardware, with a specialized FPGA, right, for the deep learning, targeting deep learning, so they have to come up with the frameworks, right? So as like the NVIDIA is doing, right? So NVIDIA, they are coming with a different architecture, right? The Tensor, the Volta, the Pascal, Turing, Ampere, right? So for this different application, they are coming up with a different version of APIs, right? So they have cuDNN for deep learning, right? And cuBLAS, right, for general purpose application for scientific computing, right? So only coming up with the hardware will not be going to be much effective, right, in terms of their market share or in terms of customer, right? So they have to ease the usability of their tools, right? If they come with the tools for the specific application, if you take for deep learning, so they have to be they have to give a flexibility for the customer who are going to use, right? They must not create the tool must not create more error, okay. And it has to give all the support for all the deep learning models which they are going to deploy on the FPGA, right? The FPGA the FPGA companies who are targeting the AI hardware applications, so they have to come up with the APIs, right? So Xilinx, they have come up with the YTCI, right? I'll discuss in my next slide, okay. Yeah. When it comes to FPGAs for AI, right? So FPGAs, they actually takes less power when it comes to when it comes to GPU. When compared to GPU, the FPGA takes less, comparatively very less amount of power when it compares to the GPU, right? Right, and also you'll get a flexibility of designing the precision and customizing your data flow and customizing your memory, right? So that amount of flexibility going to get right while you're deploying your deep learning model, while you're doing inference on your FPGA, right? Yeah. If you see here, right, there's a lot of research has been done on implementing neural on power-friendly devices like FPGA, right? So also, yeah, a lot of labs, right? So a lot of research is going on. I think in CDAC also, they may be implementing uh, the deep learning algorithms on FPGA, right? Yeah. So if you see the FPGAs, right, are small devices with a little power consumption with a reconfigurable hardware, right? So the power consumption is a issue with the GPU. So that will be overcome by the FPGA, right? Yeah. FPGAs don't have a same speed, not the same amount of research, resources of the modern GPU, but the efficient implement, right? So it all depends on how you implement your neural networks on the FPGA, right? So yeah, of course, GPUs have a lot of cores, right? So they have 1,000, 5,000, 10,000 number of cores. Right, so there is lot of parallelism happening in GPU, but what happens in FPGA is that you will get a flexibility of designing in various ways, and one important thing is right. So you need to design efficient. It all depends on how efficiently you design the deep learning models, right? So as I said, right. So this you can implement the algorithms what I said to in your design, so that you can bring you can bring the amount of the time taken for inference of deep learning models when you compare to the GPU, right? So that it's all depends on your on how on the way how you implement on FPGA, have you implement the algorithms on FPGA, right? Yeah. So that will be uh, one of the advantages you'll be getting for FPGAs if you want to use FPGAs for AI. All right. So let me give some time to read this slide. Okay, so you can take some 10 seconds to read. Yeah. So this sentence is with respect to EIE. Okay. So EIE. Okay. So if you're reading, you take this as a context, right? So yeah. Let me go ahead. Okay. Yeah. So while how FPGAs okay, bring the flexibility or designing the hardware and increasing the uh, you know uh, the amount of speed up, right? So you have a flexibility of designing the custom data flow, right? And also you can design a custom data flow in the sense you can design the hardware for as I said, right? You can design hardware for the neural networks by Facebook came in last year, in last month, and also you can change that hardware for the new state of the art model, right? So that flexibility you are going to get, right? And then when it comes to also it gives the flexibility of the designing of memory hierarchy, right? So you can use less use your DRAM, right, on your PL. You have your sorry the PS, right? You have the DRAM on your PS, right? I hope some people have worked with the FPGA Zinc devices. So you have your DRAM memory on your FPGA, right? So you have a PS and PL, right? So FPGA has a PS and PL, right? So your Zinc has PS and PL, right? So PS consists of the ARM Cortex, right? So ARM Cortex, uh, you know, CPUs, and your PL will have a reconfigurable FPGAs, right? So FPGA, so reconfigurable architecture will be in a PL, and your CPU will be in PS, right? So this has a DRAM, right? So while you are storing while you're designing, so you can store your deep learning model on this DRAM also, and then you can store your model on this on the memory available on PL also, right? So you can store on BRAM also, right? So the main goal has to be to use less DRAM here, and to use more BRAM here, right? So that will be that has to be the design goal while you're designing the hardware for specific neural network, right? And also you'll get a custom precision, right? So you can design a neural network for Intet also, and you can design your neural network with a FP16 also, right? So that amount of that kind of a flexibility you will be going to get while you're designing the deep learning algorithms on your FPGA, right? So if you see here, right, FPGAs allows you to customize your data flow to the current state of the art network, right? So as I explained here, as I explained earlier, so you can design if you design the hardware for earlier neural networks, you can change it for like assume, right? So you have a SSD for real time object detection, right? So SSD, right? So sorry, this is SSD, and you have a YOLO, right? So YOLO, assume YOLO V2 also we have, and YOLO V3 also we have, right? Uh, so V3 also we have, right, for real time object detection, right? So what flexibility you are going to get is that when you design your model through HLS or through RTL, for this YOLO V2, then after 1 or 2 months, your YOLO V3 will be launched. Okay, assume your YOLO V3 will be launched. Okay, so this has much more better the frame rate and the accuracy is better for YOLO V3 compared to the YOLO V2, right? So you can change, right, the design. So for like the hardware design for YOLO V2 can be changed to the YOLO V3, right? Right. So this amount of so this kind of flexibility you are going to get, right? So this is better, right, compared to YOLO V2. YOLO V3 is better, right? So you can use change the hardware architecture from YOLO V2 to the YOLO V3, right? So here you will be getting more accuracy, more speed up, right? So this is what the first the this thing signifies, right? And next thing is that they allow you to customize your memory hierarchy, right? We can try and increase the amount of the on-chip memory use instead of DDR, right? As I explained earlier. Okay, so you can use your on-chip memory more instead of DDR, right? So if you want to implement efficiently on FPGA, right? You can also you can also customize the precision, right? So as I said earlier, you can customize from FP16 to int8 for better instead of going for FP16 FP32, you can represent it to int8, so that your memory will be your on chip memory will be used more rather than the DDR, right? So these three are the flexible advantages you'll be getting while you using these three methods, right? One is with custom data flow, and another is with respect to custom memory hierarchy, and next is with respect to custom precision, right? So yeah, I think you'll be knowing more about heterogeneous computing, right? Right. So you have sync devices as I explained here, right? So this is a heterogeneous platform, right? So you have both CPU here and both FPGA here communicating both using the AXI, light AXI AXI light interface or AXI burst interface, right? So this is one kind of one kind of heterogeneous platform, okay? And also if you see now the GPUs, right? The GPUs in various premises, right? In your system, also in your cloud also, right? GPU will not come with only GPU, right? So GPU has to be has to come with a integrated CPU, right? So that is one of the heterogeneous kind, right? So their CPU acts as a master, and FPGA or CPU or GPU acts as a right uh, your slave. Okay, so if you see here, right, earlier there was a homogeneity, right? Only the CPU cores were used, but now we use heterogeneous computing platform, right? So you have FPGA, CPU, GPU, DSP for specific applications, right? So GPU can be used for uh, you know uh, GPU can be used for graphics application, and then DSP can be used for your signal processing, right? So your audio, audio, voice, right? So the uh, those kind of applications can be used by the DSP, and when the graphics applications, graphics rendering applications, your gaming, right? Uh, can be used on your GPU here, right? So the CPU can also compute and also can manage, right? So they allocate the task for the GPUs and DSPs, FPGAs, right? So and other specific targets, right? And also now in your Snapdragon chips, right? So they have coming up with a neural network, uh, IPs, right, on your Snapdragon chips, right? For advanced AI applications, right? Uh, so this is one of the advantage of heterogeneity, and now everywhere you have a heterogeneous, right? You can't do applications on only CPUs, right? So if you want to do many applications, you have to come with a more architectures in one chips, right? Like the zinc you have, right? So zinc is an amazing platform for the system design, right? Actually the tools they have come up with, like the Vivado HLS. So those are all the amazing tools, right, for FPGAs, right? Yeah. So as I was saying, right, when Xilinx or other companies, if they design the specific hardware for specific application, so they have to come with a platform, right? So this is the platform for the AI, specifically for AI, right? So this is for, for deep learning applications, right? So you can use, instead of designing from scratch, right? So instead of designing your IPs, your deep learning IPs with RTL, or with HLS, right? You can just use with the frameworks, right? So you have a TensorFlow Cafe, framework, right? For representing your neural networks, right? So these are the high level frameworks. Okay. So you might be having the doubt, right? So why these frameworks, right? Neural networks, right? If you are implementing neural network with a code, right? So it's very difficult to write a code from scratch, right? From scratch, right? So these frameworks will bring a flexibility, right? So it will gradually decrease the amount of time taken, and also the difficulty to write the code in Python from the scratch, right? Uh, so these are the frameworks for deep learning, and they have a model zoo, right? So they their Xilinx, I'll come with a model zoo. Okay. So the Xilinx have their own models, okay, for which supports for the DPU, right? So this DPU is a deep learning processing unit. Okay, so this is the hardware, the IP created by Xilinx, which is used for different for different applications, right? So the computer vision applications, you can use this hardware for deep learning applications, right? So no need to design the hardware from scratch. Okay. Rather than you use a DPU, right? Uh, for as a hardware, right? So if hardware is available, so you need to have the APIs, right? So these are the different APIs to use the DPU for efficiently, right? So you have AI compiler, quantizer, optimizer, profiler. Also, they have AI. They have AI library, and they have runtime, right? So to port the the bit file on the DPU, right? So this is a Xilinx a platform for AI applications. Uh, So previous to Xilinx White is AI, right? So they have a DNN DK, right? I'll come up with the next slide. So this is the DNN DK, right? So before the White is AI, they had a DNN DK. So advanced, the next version of DNN DK is White is AI, right? Uh, in YTCI, you'll get a the optimizer, right? So the AI optimizer here, right? So where you'll not get in a DNN DK, right? In DNN DK you don't have AI optimizer, right? So in this DNN, in this quantizer, optimizer compiler, they use this they implement these algorithms, right? So as I've seen here, as I've shown here, right? So they implement these algorithms, right? So they use pruning, and they use quantization in their frameworks, right? And also you have a binary and ternary nets. Okay. Right. Like Xilinx have their own fin framework, right? Fin framework, FINN, right? They have a fin framework designed to specifically meant for the binary net. Okay. uh, so that fin will be going to use the DPU, right? So the DPU, as I've shown here, right? So here, right? So that fin will be using the DPU at the back end to run the binarized neural network on this hardware, right? Yeah. So the DNN DK was also another framework before to YTCI. as I shown here, right? So this is a YTCI pipeline you have, and this DNN DK also is a platform, but that is not for edge device. That is not for cloud. Okay, so this YTCI is also for cloud. Okay, so you have Alveo boards, right, from Xilinx, Alveo boards. So this YTCI platform can be used for Alveo boards. Okay, so not only for the edge like Zinc 700 and MPSOC family, right, and Ultra 96 other boards, ZCU 102 and other boards. So those this uh, YTCI will also support for the cloud. Okay, so for the Alveo boards, right? And this DNN DK, they also had a decent. They have a quantizer, right? So they have a quantizer, right? So this quantization, this what this quantizer will do is, this represent the number, the floating point number into the int 8-bit representation, right? So this is what the quantizer will do, and they have a compiler. Okay, so which converts the your RTL code into the bit file meant for the devices, right? For separate devices, right? And then you have there's no pruning method, right? So as I said earlier, so they don't have a AI optimizer, right? In DN and DK, they don't have a AI optimizer, while unlike in YTCI, right? So in YTCI they have a AI optimizer, right? So that's one difference. But DNN DK, YTCI platform have evolved, with their compiler technology, right? So it's easily, you can easily debug the errors, and and you can see where exactly it's easy to debug and to overcome the errors, right? So that compiler technology is bit advanced. So Xilinx is working closely with the DeFi, right? So DeFi is a startup. They have also acquired in 2018, 2018, or no, I think in 2017, right? So I'm not sure with the year. So Xilinx, they have acquired this DeFi startup from, this is from China. So they have closely working with advancement with this quantizer, compiler, optimizer. So these are all their product. Okay, so DeFi, all right. So they have advanced pruning technology they have, right? And also the GPU, the DPU supported only up to 3 cores, right? So with the DNN DK, so that limited the performance. But in YTCI, uh, this problem is overcome, right? So this problem, pruning and the supporting of the cores, has been overcome, right? And also, if you see with a AI SDK also, right? So they have AI SDK library also, right? But one major disadvantage is that DNNDK will not support for other networks, right? So it only supports for few deep neural networks. Okay. When it comes to YTCI, so YTCI, they have a quantizer, compiler, profiler, optimizer, and library, right? So these kind of frameworks they have integrated with a Xilinx YTX AI platform, right? So previously in DNNDK, you didn't had a AI optimizer, but in YTCI, they have a AI optimizer, right? And also they have a the model zoo, right? So if you check with this link, okay, so you can see which all models are supported. Okay, so you can take the models from these model zoo, Xilinx AI model zoo, and then you can go on proceeding with using the Xilinx YTCI, right? So you can you can use the models which are present in this model zoo, and further you can go with the optimizing, quantizing, compiling, and right, and then deploying on the DPU, right. Yeah. So if you want to design the the hardware from scratch, okay, rather than using these platforms, this Xilinx, Vitis, or the DNN DK. So if you have if you are interested with designing your own hardware from scratch, right? From scratch in the sense, like through RTL or through HLS. So if you want to design, then you can do, right. So this DPU may not be efficient for some applications, right. So this DPU is for, so you have DPU right here, deep learning processing unit. So this deep learning IP from Xilinx, it's a general purpose, right. So you can come up with a design for specific application, right. No, it's very much difficult to design for general purpose, right. So like DPU, rather than you can go ahead and design the hardware for specific neural network, and then you can show the significant speed up, right, comparing to the DPU, right. So DPU is general purpose, right, so it's not for specific, right. So you can design the specific the hardware for specific neural network, and then you can show the significant amount of the speed up benefit when comparing to the DPU, right. So those things you can do in your projects. So let me show you the example design, right. So this is the example design. So if you see so this is done with a zinc ZC702 board, okay. If you see here, right, you are so this is on this is on PS part, and this is on the left part is a PL part, right. So this is the PL part, and this is a PS part, right. So CPU is acting as a master, and you are implementing this whole network on your FPGA PL part, right. So first thing, so what happens is that, so CPU will store the weights, right. So the weights required to compute on the DRAM, right. So here DRAM is there, right. So you can store you can store the DRAM serially, right. So like the weights for the zeroth layer, right, in this one, and the weights for the first layer in this row, and likewise, right. So second, third, right. uh, yeah. So what happens here is CPU in first phase, CPU will store the weights in your DRAM, and after that what happens is that the CPU will give the command to the weight mux here, right. So this is also the block the block implemented by scratch, okay. And also these neural networks, right. So you have networks, right. You have the zeroth network is here, first network, and so on, right. So what happens here is that CPU will say to this weight mux, okay. Yeah. So I have stored the weights in the DRAM here. So what CPU does is, it will send a message to this weight mux, right. By passing the address, right. So it will send the message. It will say the layer index, right. So layer index in a sense, if the weights has to be passed through layer 0 or 1, okay. So this 0, the weight stored here, so has to be gone to the layer 0 here, right, for the computation, and the weight stored in the first in the first the first part of the DRAM has to be gone to the layer 1, right, and second to the second, right, to the second block, right. So like this way, while computing the first layer of this neural network, so what CPU will tell to Weightmux is that, so CPU will send the index. Okay, so it will send the index, saying that now it's a time to compute the layer one. Okay, so you just send the you layer, it will tell to weight marks. Okay, so what it will tell is that, so it will take the weights from the first from the first row of the DRAM, and then at the zeroth index, and then give it to the layer 0. Okay, to compute. Okay, so it will say, by giving the address. Okay, so it has to give the address, right? So after giving the address, and the layer index, right? So what Weightmux will do is that, so it will take the it will take the weights of the first row, and then it will it will pass it to the neural network, first layer of neural network implemented in the PL, to compute. Okay, right. And once at the starting, once it sends the layer index, it will give the uh, you know um, it will send the interrupt, right? So it has to send the interrupt, right? So saying that, now it's your turn to compute. So Weightmux is sending the Weightmux is sending the weights for you from the DRAM. So now it's your turn to to compute, right? So yeah, so if we see here, right, CPU is acting as a master, and the FPGA is acting as a slave, right? So this is one example design, you so in the FPGA, right, which is from the scratch, right? Yeah, and then after it computes, right? After it computes with the weights stored in DRAM. So what happens is that, it will it will give the results to the next layer to compute, right? Uh, to compute further, and then it will send, I mean it will send again to the CPU, saying that, I had completed the I had completed my neural, the computing part, and then you can go ahead with the next layer, right? So again, the same, the same thing is repeated, right? Again, the CPU will tell, that, will send the layer index of the first neural network, and then it will send the address of the weight it stored in the DRAM, and then after that, the weights will be accessed from the DRAM by the Weightmux, and then the Weightmux will be giving that weights to this channel to compute, right? So like this way, the computation will be happening, right? So yeah, so like this way, the neural networks will be sending the results to further, right? As you see here, in if you see the neural network, right? Right, so this is the one layer, and this is the next layer, and this is the next layer, and this is the next layer, right? So when you compare this with the with the one, the example design I had shown, so this will be the zeroth layer, and this will be the first layer, and this will be the second layer, and simply the third layer, right? So like this way, you can implement, right? So this first layer will be implemented on the FPGA. Like you can use you can use your you can use C++ through HLS to design, and also you can do with the RTL, right? So if you do with the RTL, you will get more optimization, right? So because you are doing with a very low, so you'll get a complete control, and the optimizations will be high compared to the one which is designed through HLS, right? Yeah, so this was one example design I had shown. So this is only for accelerating, right? So while accelerating the inference, not for training. So this way you can design your neural network on the FPGA, right? Yeah. If you see the computing, right? So earlier you had a PC era, and then you had a mobile, right? And then now we were in now the brain inspired computing, right? So the neuromorphic computing and quantum computing will be in the next phase, right? So in brain inspired computing, what happens is the computation will be in memory, right? Rather than the like in classical, what happens is that you have memory here, and then you have a CPU here, right? So in brain inspired computing, what happens is so this will be in the same in the same place, right? So the memory will be here, and also in the computation will be here in one part only, right? Rather than, so this speed will be this time will be gone, and then the in memory computing will be done, and then uh, and then you will and then you will get a significant amount of speed up, right? So this is about the brain inspired computing, right? So you have memory stars, right? I think you might be knowing about memory stars. So where the memory and the resistors will be in one place, where the computation, right? The computation and the memory will be in one place, so that will your significant amount of you know uh, speed up will be going, and also efficiency will be much more when it compared to the classical computing, right? And also if you have a quantum computing, right? So quantum computing is completely different from the the classical computing, right? So there you will get different gates, right? So you'll not be getting the AND gate nor gate, in the classical you have, but in quantum you'll have a different gates, right? You have a Adam and gate, and some other gates you'll be able to see right in the future, right? So Google and IBM are majorly working on cognitive. IBM is was the pioneer of cognitive computing, right? The brain inspired computing. No, they were the pioneer, right? So of the brain inspired computing. But they are also in the quantum computing now. Okay, Google and IBM are also majorly working on quantum and mm, the quantum computing. Okay, so let's see in the future what may be the reality. Okay, now we can't tell, okay, how when it will be going to be implemented, and how and also it's very much difficult to transform from the classical to quantum, right? So it's very much difficult, right? So yeah, let's see so in the future what may be going to happen, right? With this all, I'll be going to end my session. So let me revise. Okay, so the session. Uh, so first, I have discussed the basic of neural networks, how the training and inference is happening, and different hardware families we had seen, the FPGA, ASIC, CPU, GPU, and then we went on through the different algorithms, right? So for efficient inference, right? The pruning, the quantization, and weight sharing, low rank approximation, WINOGRAD, and then binary ternary net. Okay, yeah. So those were some some algorithms for efficient inferencing. Okay, and then you also have we also discussed the different architecture, right? So different ASICs, different chips for specifically for AI. All right, we discussed the iris and TPU, tensor processing unit, and then EIE accelerator, right? From Stanford, targeting for different goals, right? From like sparsity, precision, and then the memory access, right? So Then we went on to discuss about the FPGAs, right? So the FPGA platform, right? So it's the Xilinx FPGA platform, right? So they have YTCI and then DNN DK, and then we also discussed about the example design, which we are going to design from scratch, which is designed from scratch, right? And then at the last we discussed some minutes on the next era of computing, right? The brain inspired and the quantum, right? Yeah. So with all, I'll end up my session, and I thank for CDAC for giving this opportunity. Yeah. So thank you.
Okay. Thank you, Darshan, for a wonderful session.
Yeah. Thank you.
Okay, if the participants have any doubt, you can post it in the chat box.
Yeah, thanks. Thank you all for your patient hearing. Okay, so I think there was something to learn in these sessions. Okay, so I discussed various concepts. Okay, so that may be new. Uh, yeah,
Okay, now I welcome Mr. Kader, Principal Engineer of ERN DCAT, to say the vote of thanks.
yeah,
Uh, so from my side and all of us here at the RNDC IT, from the faculty side and the student side, I wish
yeah,
to thank Shri Darshan for his wonderful exposition of AI implementation in FPGAs. So we feel that the future is all about energy efficiency and how to improve the computation on the go,
yeah,
right?
yes,
So
yes,
that was a really enchanting experience, and
yes,
we wish that you would come often to give us your experiences through contact classes or any way. And
yeah.
it's really an enriching experience for
Yeah.
all of us. Thank you all the participants for
1 minute, one question is coming in the chat box. Darshan, could you
Okay.
please?
questions for Darshan.
Yeah. Yeah. So with distributed, the question is with the distributed edge computing, is it possible to deploy reliable checks and balances to prevent AI-based systems from evolving into something beyond your control and propagate over the network? Uh, okay. Distributed, edge computing is also evolving, right? So recently, I read one paper on the model parallelism, right? So how you can split the model, right? As I shown here, as I shown in my slide, uh, you know, uh, you know. Uh, the model parallelism, right? So you can split one amount this model onto one core of GPU, and then you can split on this to one GPU, and this to one another GPU, right? So likewise, you can split your neural, your part of your different layers on different cores, like that you enable your parallelism and the speed up, right? So likewise, I think there are these have been implemented in specific the APIs, right? So you have a TensorRT, right? I think you might be knowing about TensorRT for NVIDIA platform and TF Lite, right? So this TensorRT and this TF Lite, so those actually they have implemented algorithms, right? Different algorithms, right? So you no need to worry about all these algorithms, right? Uh, while of course, if you're doing any research on these optimizations, if I have to work on pre-existing things, right? So like you have to go in depth of these frameworks and what exactly they are doing on model parallelism, data parallelism, kernel auto tuning, right? And some precision calibration, right? So bringing back from FP30 to int 8. So those things actually you have to take care of, right? So you have to dig deeper into the optimizations, and you can do a lot of research. But the thing is, now there is a lot of innovation happening in terms of compiler technology, right? So this here, if you see the compiler as I shown the here, right? So in YTC AI platform, if you see the AI compiler here, right? So it's also it's not only compiling, converting the one form of representation to another form of representation, but it's also doing the optimization, right? So these two are doing quantization and optimization, but these two is doing the decomposition. So this is doing the decomposition plus the plus converting from one form to another form, right? So if you see the decomposition as I shown, right? Low rank approximation I shown in this slide, right? So this AI compiler in the Xilinx Vitis platform, it's doing this kind of decomposition, right? So your decomposition complex into two simpler, right? So yeah, so that is doing by the AI compiler, right? So yeah, compiler also is playing a huge amount of role in terms of optimizations, right? So you have Google, right? So Google is also doing more amount of research on the compiler technology, right? So you have Google have their own, they're coming up with a own MLAR technology, compiler technology, right? I'll post it, MLIR, right? So if you can search, right, with this MLIR. So what MLIR is technology is that of mm, if you want to deploy your model on different targets, like FPGA or ASIC or GPU CPU, right? So this MLIR will bring the flexibility to run your model on different target hardware, right? So while if you see the compiler, right? So before compiling to the target bit file, to the target representation, you have an intermediate representation, right? So let me draw and show you, right? I think there's some issue with the pen. So yeah, as I was saying, with a compiler, right? So assume I think it's difficult to draw here. So yeah, so in compiler, what happens is while converting your assembly to bit or some high level to some low level. So what happens is that before converting the assembly to the target target specific bit code, so it has to go to the intermediate representation, right? So before the compiler converts one form the assembly to the bit file, so it has to go to the intermediate representation, right? So what MLAI technology does is that before going to the bit file, so it will go to the intermediate representation. So from that intermediate representation, it will go, it will do, it will generate the target specific application, right? So if application, if you have a FPGA, then you can, that MLAR technology will transform the intermediate representation to the bit file which is required for a FPGA, right? Likewise for different for different target hardware, right? For GPU, CPU, right? So till intermediate representation, it's all the same, right? So same thing happens for if you want to compile it for different target hardwares, right? But in different but previous to MLAR, it was not like that, right? So you need to compile only for specific application, right? So like the you have you have a compiler right here, so you need to compile it for only for DPU, right? So this DPU, this Xilinx DPU, right? That compiler will not generate a code for different hardware, right? But this MLI technology will do that. Okay, so I hope Mohan, I hope I had given some, I had cleared your doubt and given extra knowledge also. So pruning is platform specific. So I think no, it's not a platform specific. It's a model specific. Okay. So what is model specific, right? So you have a deep learning model, right? As one neural network. If you see, the pruning is not a is not a hardware specific. It's a model specific. Okay. You can't implement pruning for some neural network. Okay. Pruning may reduce the accuracy to gradually for one neural network, and for other neural network it will not be like that. Okay, it will not be the case. Okay, so this neural network will be random, right? So it's all random. Okay, it's randomly it's happening, random weights. Okay, so you can't have a complete control on you can't have a complete control on to decide which whether pruning is whether it's satisfied for this network or the other. So you have to do the trial and error method, right? So you implement pruning for one network, and then you check whether it's working well for this network or other, right? But for the quantization, as I shown here, right? So this quantization, but I didn't cover in depth about quantization, but this quantization, right? The quantizer I have, right? So this quantization is used for all the hardwares. Okay, in general, for all the neural networks, for all the hardwares. Okay. So this ST microelectronics, and Qualcomm, and Google, the NVIDIA, they all have quantization implemented in their tools, right? So quantization will be supported for all the target hardwares and all the deep learning models. Okay, I hope I answered your question, Matthew.
Okay. I think there are no more questions. So thank you once again, Darshan, for sparing time with us and given valuable insight into the AI, which is we can implement it using the FPGAs.
Yes.
And thank you all the participants also for being there, and we expect you in the coming sessions also. Thank you once again all. Thank you.
Yeah, thank you, ma'am, and thanks to the CDAC Trivandrum for this wonderful opportunity. And I hope there was something to learn, right? To learn from your students. So with this I conclude.
Thank you, Darshan.